Hey guys, I hope you all are doing good. In this lecture, we will try to understand what are logic gates and how we can solve any Boolean expression using the logic gates, right? Before I start, let's try to understand what's the purpose of logic gates. So, by now, I hope you understand that what we are trying to do is we have a problem and we want the computer to understand it, right? And in order for us to do that, we convert it into some kind of a Boolean expression, right? Which is in terms of zeros and ones, right? So a computer can understand it. But how can a computer really, we can like use the computer to do it? That is where the logic gates come in play, right? So at the very basic level, the computers are made up of these logic gates through which we input zeros or ones values, and then they can do operations for us, right? Which could be multiplication, addition, and many more, right? So that's the basic idea. At the very basic level, a computer is made up of gates joined together. So what is a logic gate? A logic gate is a digital circuit that takes one or more binary inputs and produces a binary output, and each gate implements a specific Boolean operation. So I hope you understand and have an idea about all the Boolean expressions that we covered, right? We had not, and, or, right? And I'll explain the NAND and NOR to you guys. They're also very simple to understand. So the NOT gate is very simple, right? We just simply draw it as this kind of a triangle with a circle on it, right? So whatever input you take, let's say if I take the input 0, it results in a 1. If I take the input 1, it results in a 0, right? Second one is the AND gate. So what basically it does is I input two variables, right? Let's say it could be a variable A, B. Now, what are these variables again? They are basically some values, right? They could be 0, 1, both zeros, etc. So what it does, it basically does the dot of it, right? And so let's say if I had 0, 1, then this would be 0, right? 1, 0 would be 0 again, 1, 1 would be 1 in this case, right? So I hope you understand the representation of the AND gate. Third one is the OR gate, which is basically just A plus B, right? So I hope you understand this one as well, right? It is kind of like kind of similar to the AND gate, but it has this pointing arrow kind of a shape for it, right? So these are the three basic gates. Now we can form any equation just like I said, right? First, what we can do is we have a problem. We can form a truth table for it. Second thing, we can convert it into the SOP or the POS form. And using that SOP or the POS form, we can basically simplify it and then use the logic gates to basically represent it, right? And that is how we can basically form a very simple computer or a very simple computer that can solve a very basic problem, I should say, right? Okay. Now let's try to understand what is the NAND gate and the NOR gate, right? So the NAND word is basically made up of NOR plus AND. So the basic point is we take the AND of the variables we have and then we do the negation of it. In NOR, what we do is OR plus AND. Oh, sorry, this should be negation. This should be not plus and this would be not plus OR. So in NOR, we basically do the OR of the variables and take the negation of the entire operation we have. And in the NAND, we take the AND of the variables and take the negation of the entire operation. So if you take a look at this, I had the variables A, B. I did the dot, which is I did A and B and then the negation of it. In this case, I did A or B and did the negation of it, right? Why do we have these extra gates if we can use these different gates? The basic point is that we can actually use just this NAND gate to represent all these three operations, right? So just using this one gate, we can form any operation that we want. And that is exactly why we have this operation over here, right? I'll explain in the later part of the video where I'll show you how NAND corresponds to NOT and OR. Okay, so I hope you have a general idea about what are logic gates and what's the basic purpose behind them. Now let's try to understand how we can use, let's say if we have been given a binary expression or a Boolean expression, how can we convert it into a logic circuit? Okay, now let's try to understand how we can implement or convert a Boolean expression into a logic gate circuit, right? So I've been given these three variables. So the first thing that I do is I write them down using these three values, right? So A, B, C, these are my inputs. The first thing is, if you see that I'm supposed to do B dot C, right? Whenever I see a dot, that means I need to do a AND of both of them. So that means I need to put both this and C in throughout the AND gate, right? And when I do B dot C through AND gate, it results in a B dot C. And then what I'm supposed to do is I'm supposed to do a plus, or I should say OR with the A. So what I can do is I take this A, I take it over here, and then I put this entire value through a OR gate, which will result in A plus B dot C, right? So a very basic example, but I hope you will be able to understand or solve complicated circuits as well, right? This is not very difficult to understand. I'll be giving a bunch of questions towards the end for you guys to solve. Okay. Second thing that I wanted to explain is the gate equivalence, right? So just like I said, right, the NAND gate or the NOR gate are called the universal gates, right? So basically, we can use them to represent any of the three operations, which is NOT, AND, OR, right? And this is the equivalence. This is what it means, right? NOT A can be written as A NAND A. You can also check this using the truth tables if you want to confirm, right? A and B can be written as, I should say, and is A NAND B, NAND A NAND B, and A or B is equal to A NAND A, NAND B NAND B, right? And I know this sounds kind of complicated to understand, but the basic point is, right, just a basic summary of this entire thing is that using just the NAND gate, I can form any of these expressions. And then if I want to convert it into logic gates, just using the NAND gate, I can form any complicated expression that I want, right? This is kind of helpful for us because just using just one type of a logic gate, we can build circuits for our purposes, right? Okay, so I hope you were able to understand how we can convert a Boolean expression into a corresponding logic gate. Now, I'll be giving a bunch of questions for you guys to solve. Okay, so I've given a bunch of questions on the board. Right, the first one is you basically need to figure out what is this equation, right? So you've been given this gate, and you need to figure out what is the final equation. Second one is you just need to convert this into a logical gate expression. And the third one is that I want you guys to build a NOT gate with the NAND gate, right? I already told you what is the expression for it. So you just need to convert it into just using the NAND gate, right? And this is how we represent a NAND gate, right? It is basically just an AND with a dot in front of it. Okay. One more point is that it doesn't matter that it is okay if you input like multiple values into the same gate. Right? So for example, I can do this, like 4 values into the same gate. So let's say I have A, B, C, D. Inputting into the AND gate together, I get A dot B dot C dot D, right? So there's no restriction that you can only input 2 values into it. You can input as many as you want, right? So that's it for this lecture. In the next lecture, we will try to understand how to simplify expressions, right? So I'll see you guys in the next video.